In your problem set, I'm going to ask you to prove that the number of scheme programs is countable. And I'll tell you the hint for that. Every one of your scheme programs has a certain number of characters in it, right? So we can list all the scheme programs by how many characters they have. All the scheme programs with 1 character, all the scheme programs with 2 characters, all the scheme programs with 3 characters, right? So I'm making a list. So what about the programs, say, that have 100 characters? How should I order them? I can just do it alphabetically or something. I mean, it's not so hard to order programs. You make a list of them. You make a function that goes down from 1 to infinity. But what about the things that programs want to do? What about functions that programs want to compute? That's a lot harder. So what I want to convince you of is that there are more things to compute than there are programs to compute them. And the idea here is an idea called diagonalization. It was one of the main things that Cantor used to prove that the real numbers are not countable. And it's going to come up in this example. And I'll do it real briefly just to give you a sense of it. And you'll see it again in recitation. As I just mentioned, you can count all the scheme programs. You can number them. This one's number 1. This one's number 2. This one's number 3, right, in order. And I'm going to number them down here. Programs. Okay? Over here, I'm just going to list the numbers 1, 2, 3, 4, 5, 6, etc. And I'm going to fill in this chart in the following way. This program number 1 that we called program number 1 can work on any input that we put in. We can put in the number 1 as input. We can put in the number 2 as input. In fact, let's think of these numbers as representing programs again. So we're putting in programs to this program. You have a scheme function, and you type in a program to it as input. When it says, please type in your input, you type in program number 1. And your scheme function is going to either say yes or no. It's either going to stop and say, yes, I like this program, or no, I don't like this program. So these are all the programs that just end up saying yes or no. They don't do anything clever except saying yes or no to an input. So let's put in some values. Say it says no to this, yes to this, no to this, yes to this, no, 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 etc. And I can fill in this chart with zeros and ones. Now, if there's something a little fishy with what I'm saying, can I really fill in this chart? Why not?
It goes on forever.
Okay, it goes on forever. That's true. But I could at least describe filling it in. Is it even worse than that? What if I got up to this spot right here? Program number 6, I put in program number 1, and I wait to see whether it says yes or no. And I wait. And I wait. And I wait a little more. And it's July, and ADU is over. And I go check on how you're all doing 10 years later down the road, and everybody's doing fine, happily married with lots of kids, making lots of money, and doing their dream, and everybody's just completely content. And I say, hey, by the way, that program number 6 is still running on input number 1. I'm still not sure if it says yes or no. All right? Then we're all dead, and it's 10 generations down, and the Earth gets destroyed. There's new civilization. They find my little program running on a microchip that's sitting there, and it's still running and running. And this runs forever and ever and ever. How do I know it's ever going to stop?
Wait long enough.
I wait long enough, right? It might never stop. So it's possible that one of these things, I might not be able to fill in. But for the purposes of this argument, let's just say that, look, if it accepts it, I'll put a 1 in, and if it doesn't, there's a 0. And I might not know that. But here's what I could do to conceivably fill in this chart. I could run each one of these programs for 1 step. And then I could run the second one for 2 steps, and then run the first one for an additional step. Then I'll start the third one. I'll run this for 1 step. Then I'll run this for another step, and this for another step. I could run them all at the same time, adding 1 step each time, so that sooner or later, if the thing had a 1 in there, I could fill it in. In other words, I wouldn't get stuck at one program waiting and waiting and not be able to fill in the rest of the table. I would do 1 step of this program and then add an extra step to all the others I had done and then start with the next one. So that sooner or later, if it's going to stop and say yes, I'll be able to put a 1. And if it's going to run forever, it'll never put anything in there, but I won't have to worry about us getting stuck along the way. Does everyone understand that trick? That's sometimes called dovetailing. It's a trick to get all these things to run at the same time so I can convince you that conceivably I'll put all the 1s in at some point. All right, so
I'm lost. You're saying that program 6 and position 7 has an infinite loop to it.
say program 6 on input 1 has an infinite loop.
Okay.
And I don't want it to get stuck there because then I couldn't convince you that I can...
What happens when you hit 6, 1?
So here's what I do. I run program 1 for one step on this input. Okay, and then I run program...
2 for 2 and then 1 for an additional 1.
I run program 1 for this one on one step. Then I run program 2 for this one. Then I run program 3 for this one. And every step along, I add one step for each of these programs.
What happens when you hit 6, 1?
I do one step of that program. And then I do one more step for each of these on all of these inputs. And then I continue with program 7. Right, I leave it as a question mark. Right, and these things eventually get filled in when we need to fill them in. All right, I don't want to spend too much time. This is actually a subject in theory of computation, but I want you to see this one idea of diagonalization. Now, let's say I've done this. I now have this big chart filled in. Okay, I have all these programs listed here, every single program in the whole world listed here. Okay, I have all the inputs listed here, and I have, look at these things. A particular row here represents a computation. It represents a list of programs that this program accepts and a list that it doesn't accept. In particular, a list that it accepts. I want to convince you that there is a list of acceptance that isn't in this table. In other words, there's a computation like this that none of my programs are doing. Okay? Each one of these infinite sequences of zeros and ones represents a computation, represents something that you might want to write a program to do. I'm going to convince you that after you've listed all your programs down and I filled in this chart, there is a particular computation, a sequence of zeros and ones, accepting or rejecting these inputs that doesn't exist in this table.
All your programs are unique.
All my programs are unique, yeah. But even if they weren't, it would be okay. I mean, I could have two that have the same computation. I'm going to convince you there's a new one that's different from all the ones in my list.
Oh, I know how it works.
Right. I don't think I need to say that these are unique. Even if they're the same, it's okay, I think. So here's what I'm going to do. I'm going to go down. I'm going to go down this diagonal. That's why it's called diagonalization. And I'm going to create a new set of zeros and ones. And I'm going to convince you that that set of zeros and ones doesn't exist in my table anyplace. That means there's a computation, and none of my programs compute it. That means there's a program that's missing from my list. In other words, there's a computation, and there's no program that does it. Here's how I'm going to do it. Every place I see a 0, I change it to a 1. Every place I see a 1, I change it to a 0.
What happens if you hit a question mark?
Zeros or question marks change to... Change to ones. Ones change to zeros.
You have scattered question marks.
There's scattered question marks, right?
This one and the diagonal.
Yeah, I think we'll have to turn question marks into ones. Zeros and question marks will turn into ones, and ones will turn into zeros.
There's a problem there.
Is there?
Yeah, if you announce that a question mark is a 1, and then you put a diagonal with a 0 there.
Oh, yeah.
Sometime along the line, the question mark may announce, hey,
Right. It might go back the other way. Right, it's true. Yeah. I'm trying to avoid technicalities, and I'm getting more technicalities. All right. I can't fix that easily without changing the way I want to do this. So let's say no question marks. Yeah. Let's say no question marks. Let's say these are all, say, zeros and ones. It's not so realistic, but at least you'll get the notion. If I go down this diagonal and I change the zeros to ones and the ones to zeros, then I get a new list of ones and zeros. And that new list, here, let's write it in. It's 1, 0, 0, 0, and then it would keep going. This list is different from this one. It's different from this one. It's different from this one. It's different from all the ones in this long, infinite list of programs. That means... Yeah, I guess you don't need to really, but you could. In other words, it's a list of zeros and ones that isn't in there yet, which means that there's some computation that exists, and there's no program that does it. Yeah.
I've seen this before, and I understand how you generate the new number, but I'm never really sure how we know if we have an infinite list that is a unique value. that we just generated?
Because this value's got to be different than every one of the ones that's already there.
Different than the ones in the diagonal, but what about ones that were
Yeah.
in row 29?
In row 29, it'll differ from the 29th row in the 29th spot.
Okay.
Okay? It'll differ from row 152 in the 152nd spot. Right, right. So it's going to be different from all the other computations that's there, and therefore there's a program that doesn't exist. Anyway, the main idea I want you to get here, you'll see this in more detail in a more rigorous way next in recitation, but what I want you to get the sense is that this idea of diagonalization does connect back to programs, and it's not just a completely abstract idea. And you'll see it again in more detail in theory of computation. The conclusion is that there are things that you want to compute that there are no programs for. That if you try to list all the programs, and you think you have them all listed and numbered from 1 down to infinity, that there's some computation that could be defined, and there's no program that connects to that computation. That there are more things to compute than there are programs. That's a good way of putting it. And yeah.
The order of infinity is greater than the number of integers.
The order.
There's more computable functions than there are integers, than there are programs. There's more things to compute than there are programs.
Are you allowing programs to have data nested within them, such as a program which, for example, multiplies any input by 2?
Yeah, include anything like that, right. Oh, you mean things that don't just say yes or no? You mean, what do you mean?
Yeah, that's what I mean. I'm not quite clear what you mean by program.
Here we're talking programs that do very simple things. Programs that take an input and tell you yes or no on the input. But that's an even smaller set than programs in general. And
you could still do the same thing and just change each of the outputs by something.
right, you can make a program with output turn into something with yes or no. You could do that. All right, I should say, I promised at the beginning that I would try to do lecture notes for all these things, and I do have new lecture notes that I printed out, and you can look up these things, and hopefully I will keep up to date here if I have time to always give you guys stuff you don't have to scribble while I talk. Okay, this is a topic which you'll see again and again. Maybe the most common thing you'll see for the rest of the semesters. You'll see it in Java, you'll see it in algorithms. This is a topic that talks about how to measure how fast functions are growing. And it's fundamental in algorithms. In the very, very early days of algorithms, somebody would come up with an algorithm to do something. They'd publish a paper. They'd do some experiments. They'd print the results, kind of like in a laboratory setting. They'd say, I ran it on this computer, on this kind of input, and here's how many milliseconds it took. And it's hard to make a comparison between that and somebody else's paper if they ran it on a different machine, or they had a different compiler, or they had a different implementation, or they used a different programming language. So soon after that, the theory kind of came up to give a solid foundation, and we compare algorithms not by just experimenting and looking at the actual number of milliseconds, but by somehow looking at the algorithm itself and saying this takes a certain amount of time independent of the underlying implementation. And we compare algorithms based on that criterion. And that's what this theory is all about. It's about trying to get a metric for how fast functions are growing. And those functions are typically coming from how long a particular algorithm is taking. All right, so let's do an example. We're going to do a very, very well-known sorting program called bubble sort for a second. We're going to calculate how many steps this takes. Here's how the program works. You put a bunch of numbers up like this in a list, and you compare the first two things in a list. And if you'd like to make this in ascending order from smallest to highest. So if the first one is bigger than the second one, you want to switch their locations. Okay? So in this case, that becomes 6 and then 8. And then you continue going down to the next pair, 8 and 2. So you get 2, 8. 8 and 10. 10 and 5, 5, 10. That's called one bubble procedure. It doesn't sort the list yet. What do we have to do to sort the list? Right, we have to do it again. So if we did it again, what would happen? 2, 6, 5, I'm going to do the whole thing, 8, 10. Okay, and then we have to do it one more time, it looks like. 2, 5, 6, 8, 10. All right, let's analyze how much time this takes. How many steps does this first bubble procedure take? Let's say comparing are the things we're counting up. How many comparisons? One comparison here, one here, one here, one here. If there's n numbers, then it's n minus 1. How much does the next one take in the worst case? N minus 2. How come only n minus 2, not n minus 1? Because this 10, what do you know about it? It's definitely the biggest number. When you're finished with a bubble procedure, you can prove that the biggest number is sitting at the bottom. And the other numbers bubble, so to speak, upwards in some less predictable way. But the heaviest one sinks to the bottom. Therefore, when you go next time, you never have to compare this one to this one anymore. That's a wasted comparison. So on the way down here, we do at most n minus 2 comparisons. And where is this going?
N times n minus 1 over 2.
This is the triangle numbers again. Right? Why did I spend so much time on them? Because they come up all the time from algorithms as well. This is an algorithm that takes time proportional to 1 plus 2 plus 3 all the way up to n minus 1, which you know equals n times divided by 2. All right, that's the complexity of this algorithm, of this bubble sort algorithm. It's not too hard to analyze this algorithm, but now we want to get a sense of what the overall time complexity of this algorithm is. We'd like to give it some kind of categorical value. In this case, the categorical value is going to be, this is about n squared. The about n squared is the part that I'm going to formulate and formalize in these definitions that are coming up. All right? Are there questions about this so far? Right.
This is always the worst case.
This is worst case, right?
And we're ignoring the time to flip-flop it. We're just looking at the comparisons.
Right, although if we did the time for flip-flopping, it would double this. And the idea of this formalization, it's a good question, Doug, is that doubling or quadrupling or any constant change won't affect our category of this algorithm. It would be in the same category. Okay, questions about this? Yeah, Chris.
Calculating the number of run, the number of sorts that's required through a given list, is it, how do you come up with that? The number minus.
You mean how many bubble procedures we actually have to do?
Yeah.
Well, since every time we do one, the correct number sinks to the bottom,
It's
1, 2, 3,
minus 1.
4, n minus 1, right.
We just got lucky in that this was done in 3.
Sometimes it gets done earlier and you can put a flag in and say stop. If the last one didn't change anything,
Worst case is n minus 1. Right?
that's right. That's right. All right, other questions? Okay. Here's a very, very dull definition, but we'll do some examples and bring some life to it. We say that a function is big O another function if and only if there exists a C and some number such that this is in the notes and in your book. You don't have to write it down. Just look at it, and then we'll think about it. I'll read this off, but then I'll explain what it means in reality. F of x is big O of g of x. We say that one function is bounded above by another. This function this function g is an upper bound for x. It bounds it on top if, basically, there's some constant, some fixed number times the g, which is always bigger than the f.
For large enough x.
As long as you're past a certain point, as long as you're past x sub 0. Now, this is completely obscure if you see it for the first time. So let me give you an example from what we just did. Here's a function. Here's our f function. f of n equals n squared over 2 minus n over 2. And I want to convince you that this function, that f of n, is order n squared. That it's bounded above by n squared. According to the definition, the way to do this is you have to find a constant so that the function you're interested in is smaller than that constant times n squared. You want to show that n squared over 2 minus n over 2 is smaller than or equal to some constant times n squared. What constant can I use to get this to work? 1. Right? This is always less than n squared, because this is half of n squared, and this takes away things from it. So it's completely straightforward that this function is order n squared, because 1 times n squared is bigger than this for every single n in the whole world, n bigger than 0. So the x0 here would be 0, anything bigger than 0, and the c would be 1. If you want to go through these definitions and show that something is order something else, you have to find the c and find the x0.
With the theta notation, we had both upper and lower bounds, but this looks like we've only got a...
We got an upper bound here.
So we could say that... F
Yeah, when did we do theta notation?
log in if we wanted to.
Oh, you did this thing already. All right, so here's the next step. All right, so I'm going to zoom along, and you're all thinking, oh, I was just getting it. Don't zoom along. All right. Whether you got this last month or not, I don't know how much they did on this, but this is an upper bound. The very, very same definition looks like this, but this is reversed. So that means omega is a lower bound. It means it's at least as big. And if it's both this and this, we say it's big theta. That's what it really means to be in the category, that it's bounded above by n squared and it's bounded below by n squared. If it's both of these, we'd say it's big theta. So let me convince you now that this one is not only big O n squared, but it's also omega n squared. This is what we have to do. For me to show you that this is omega n squared, I have to show you that this function is bigger than something times n squared for all n past a certain point. Well, it's not going to be bigger than 1 times n squared because it was less than 1 times n squared. So to show that it's bigger than something times n squared, you better use a smaller number than 1. So what number is going to work there?
1/17.
Probably 1/17 will work. How do you know 1/17 will work besides if you're a 17 lover? What number really works? That's easy to see. A third. Does a half work? It doesn't, right? Because a half n squared is going to be bigger than a half n squared minus something. So Sam just says, well, let's take something that's smaller than that. Is this true?
For large enough n, yes.
Could you figure out whether this is true or not, and how would you figure it out?
We're only worried with large n?
We're worried to make sure this is true as soon as n is bigger than a certain number, and you can tell me what that number is. That's the x0.
Okay.
As long as it's going to be true past a certain point, this is okay.
And it can't be 0, is that sort of part of it?
What can't be 0?
It can be.
The constant?
The constant can't be 0. The constant has to be bigger than 0, yeah. Right.
No, it could be 0, but you're not going to get a large theta. You'll just get a large omega.
Right, that's true.
Does the constant have to be positive?
In these definitions, we always use a positive constant, yeah. All right, so how do you figure out what n is going to work here? You can do some algebra here, right? You could go ahead and manipulate this around until you had something n greater than or equal to a number. Should we do it?
Sure.
Let's do one. So, okay, so how do we manipulate this to figure out this is true for all n greater than something?
Bring the 1/3 n squared over to the left.
All right, so I get
N squared over 6 minus n over 2 is greater than 0.
okay, everyone see what I did? We subtracted a third n squared, And a half n squared minus a third n squared is a sixth n squared.
Multiply by 6. Squared minus 3n is equal to or greater than 0. Divide by n minus 3 is equal to or greater than 0. N is equal to or larger than 3 will satisfy it.
Okay, as long as n is bigger than or equal to 3, this is all going to be true. You can always find that number that it's going to be true past that by manipulating this algebraically once you guess a constant that actually works. And depending on the constant you guess, this number may be bigger or smaller. And you can calculate it. They come in pairs, the constant and the value after which it starts being bigger than. Okay. Just a little review before we state this general theorem Sam just said. Who wants to try this? Let's see. I'll help. Tony, you want to do it? I'll help you. We're trying to show that this is order n squared. We want to show that n squared over 2 plus 3n over 2 is smaller than or equal to something times n squared. What should that something be? Okay, let's figure it out. Here's a surefire way to do this. I know that n squared is bigger than n squared over 2, right? Is n squared bigger than 3n over 2? Eventually. Is there an easy... If I thought of this as n squared, that means this is like 3n squared. So 3n squared is bigger than 3n over 2, right? Everyone believes that. So why don't I do this? Why don't I use 3n squared to handle this, n squared to handle this? It gives me 4n squared. This is definitely bigger than these two, because one of the n squares handles this one, and one of the n squares handle, and 3 of the n squares handle this one. Right? Make sense? All right, so this, therefore, is order n squared. And you could do a similar thing for the omega case. It's even easier in the omega case here.
There's no reason to look for a number less than 4 reasons.
No, there's no reason at all. Right. Right. Don't go out of your way to look for a smaller one. This is bigger than what times n squared?
1/2.
Agreed? In this case, the omega was the easier part. Here, the big O was the easier part. The point is, these definitions are formalizing the idea that we don't care about the constants. We care about what happens after the numbers n get very, very large. We don't care about the 2 or the divide by 2 or the 3. And this is a formal way of saying that we don't care about that. Okay, let's do...
So do we need to state what the, for n greater than whatever?
In this case, it's true for all n. So the greater than whatever is just going to be 0. This is true for every n in the whole world. And a lot of times you can do it where that past a certain point is just past 0.
N is a fraction close enough to 0, it's not true.
So you can say n bigger than 1. It's certainly true for n bigger than 1. Okay, I'm going to do one more, what I think is a straightforward example. Then I want to do a harder example to show you how much manipulation you might need in order to do these things. So let's do this question. This is what Sam was talking about a second ago. Here's a polynomial. Sam says, and he's correct, that if you have a polynomial and you want to know what the order of it is, what the complexity of it is, just go to the part that has the biggest exponent, ignore the constant in front of it, and that's what it is. So this should be big theta n to the 4th. And that's true, and you can prove this theorem. All right, so let's just see why and how the proof goes. We won't prove it, but I'll give you the intuition. Same as we did before. This is going to be smaller than or equal to 2n to the 4th, another 5n to the 4th, another 1n to the 4th,
Plus 1n to the 4th.
another n to the 4th. So how many does that make altogether? 1, 2, 7.
8, 9, 15. Just put in 17.
It's smaller or equal to 9n to the 4th. You can always go ahead and dominate these terms by this major term. All right? All right.
And that'll work for greater than or equal to 0.
Yeah, greater than or equal to 1 at least. Yeah.
Can you add that up again?
2n to the fourths here, 5n to the fourths here, 1n to the fourth here, and 1n to the fourth here. You don't really need to put 1 in for this. It's just overkill. But
Put in 7 n to the fourth for the constant as well.
you could do that, and then it would be true for
Everything.
right. You can make it 16. Not quite 17.
It's so close to 7.
We might as well make it 17. All right, let me ask you a question. Is 2 to the n big theta 2 to the n plus 1? Here are the two parts. That means 2 to the n is bigger than or equal to some constant times 2 to the n plus 1, and 2 to the n is smaller or equal to some other constant times 2 to the n plus 1.
Well, that would just be the constant. I mean, n plus 2 to the n plus 1 would be the same as 2 to the n times the constant 2.
Okay.
And we ignore constants, so that would be...
Well, you can't make, you're making an argument on the intuition from the theorem. So go back to the actual theorem. What should the C be to make this true? You're saying the right thing, but is there a C that makes this true? 1 half. These are strictly equal when C equals a half. Right? Here, this is true when C equals, well, 1. So here you use a half, here you use 1. So they are big theta of each other. Another question.
Why did you choose 2 to the n? Is that true for 2 to the n too? 2 to the n is the order of 2 to the n.
Yeah, sure. Absolutely. Right. How about this? Is 2 to the 2n, let's just do big O. Is 2 to the 2n big O 2 to the n? Is 2 to the 2n smaller than some constant times 2 to the n?
No.
How do you figure this out?
Divide both sides by 2 to the n.
Okay, let's try that idea. If you divide this by 2 to the n, what do you get? 2 to the 2n divided by 2 to the n. You subtract the exponents, you get 2 to the n. So is 2 to the n less than or equal to a constant for any constant in the whole world? Well, after you get past a certain point, this will always be bigger than any constant. So you're dead here. This is not order 2 to the n. Definitely not big O 2 to the n. Okay? Because no matter how big a constant you pick, this will eventually be larger than that constant. Right. A good, fast way of deciding how to compare two functions because of this trick, did you see how we divided there? A good, fast way is to take the functions and divide one by the other. So, for example, let's compare these two things, 2 to the n and n squared. Remember a problem set on this? Which one of these is bigger than the other? For what n? Remember you proved that? Well, there's a reason. If you could prove something like this, then what do you know about n squared? N squared is less than or equal to 2 to the n for all n bigger than 5. That means that n squared is order 2 to the n. Well, that's not so interesting, but actually it's strictly less than, right?
Why did you put in n greater than 5 on the problem set? You can make it n greater than 4.
No reason. Typo. This strictly less than, if you can get something strictly less than, then instead of saying big O, we sometimes say small o. And that means it's not only bounded above, but it's bounded strictly above, that it's really smaller than, that it has no chance of ever being the same.
It still requires the restriction on n, but no restriction.
It's the same exact definition, except without the equal sign on the less than, just strictly less than. So it means it's a real upper bound that you'll never ever reach, that you're definitely less than.
But 2 to the n is so much bigger.
Right.
At high numbers.
No surprise, you're saying. Good. It shouldn't be. If you switch this around, if you try to show that 2 to the n is order n squared, you won't be able to do it. 2 to the n less than or equal to some constant times n squared. One way to show that you never can do this is to divide both sides, just like we did before. And then we have to show that 2 to the n over n squared is smaller than or equal to a constant c for all n past a certain point. One way to do this is to take the limit of this as n goes to infinity. Put in very large numbers. If this limit gets bigger than a constant, then you can never do it. Then you won't get a big O there. But if the limit equals a constant, then you can use that constant here. So this limit goes to infinity. And you can go back to calculus and use all the tricks you can possibly think of to figure out limits in comparing one function to another. Take the function, divide it by the other, figure out its limit as you go to infinity. That's a sure way of comparing one to the other, whether one is big O of the other. And you can use all the powerful theorems that calculus gives you about limits. Okay, questions about that?
Well, with that, is this sufficient where you have it now, or would you actually have to do some algebra?
You'd have to do this limit.
Well, that's infinity over infinity. And you can deal with that by taking the derivative of both of them.
Yeah, I'm not sure. Did you guys learn how to take limits of things that turn out infinity over infinity? Maybe not. But I'll tell you a theorem I'll tell you the only theorem that's particularly useful here. That if you get a limit where when you plug in infinity, you get kind of infinity on top and infinity on the bottom, then there's more or less, there's a theorem that says, take the derivative of the top and the derivative of the bottom and redo the limit. And if that ends up being straight infinity, then this one's straight infinity. If that ends up having a real limit, then this one has a real limit. The thing about taking derivatives is that it makes it simpler. The derivative of this is approximately 2 to the n. It's 0.7 times 2 to the n, more or less. And the derivative of this is 2n. Then you can do the derivatives again. The derivative of this would be 0.7, 0.7, 2 to the n. That's the second derivative. The second derivative of this is 2. So that limit goes to infinity. Therefore, the original limit goes to infinity. That rule is called L'Hopital's rule. I'm not sure L'Hopital discovered it, but it's called his rule. One of the first things you do in an algorithms class is talk about sorting. And when you do sorting, you talk about actual algorithms for sorting, like we just did, where the triangle numbers come back in. But another thing you do about sorting is you wonder, hey, what's the minimum amount of time it's going to take me to sort things? I know I can sort things in n squared. I just showed you that. But what's the minimum amount of time? Okay, what am I trying to beat? Well, you're trying to beat n squared, but how much better can you do? Can you get down to n? Well, you can prove that if you're using comparisons to sort, we won't do the proof here, but you can prove it in algorithms, that it takes at least big theta n log n to sort numbers, counting the comparisons. You can't get down.
The best possible.
Can't do better. Right. It's very rare that you can prove an optimum thing like this for an algorithm. You can always get an upper bound on the time for an algorithm by exhibiting an algorithm. But to say an algorithm needs to take this amount of time, you really need a clever argument. And this is a very clever argument. It uses binary trees. And it proves that the minimum number of steps to sort requires n log n. That's assuming you don't know anything about the numbers, that there's no restrictions. If you restrict the numbers, you can actually do a little better. But if you don't restrict anything about the numbers, n log n is the best you can do. Now, where does this come from? What really comes out of this proof is this, that you need this many steps, the log of n factorial. That's what really comes out of the proof. And then there's a whole big stage where we take the log of n factorial, and you convince the class that that's really the same as big theta n log n. This comes up much more often in algorithms than you'll see it in other places, because logarithms come from trees, and n factorials come from permutation. So it's basically a binary tree of permutations, and that's where that comes from. But I want to convince you, and here's the main thing I'm doing now, why this is the same as this. Why log of n factorial is the same as order n log n. And we're going to work with the definition, and we're going to work with some algebra, and you'll see how mildly hairy some of these proofs can get. Okay, are there questions so far? Yeah, Tony.
Well, you said that best case you can only get n log n for sorting.
Right.
And for theta, that's true. But depending on what numbers you have, the actual execution of it, particular instance, could happen in less time than n log n.
Yes. Yes. We're talking about the overall algorithm time, which means the worst case. Yeah, right. I mean, a particular instance where, say, the numbers happen to be sorted, and your algorithm just looks at them quickly and checks, and that would be done in linear time, in order n time. But that doesn't solve the problem. That just gets lucky. Right. You're 100% right. All right, so let's get back to this. How do we show that this is going to be big theta n log n? Yeah, Neil.
Why don't you just leave it as log n factorial? Why reduce it to...
Oh, because, okay, I'll leave it as log n factorial. And I want to know where this compares to n squared, n, and 2 to the n, and n log n. These are kind of the stars in our universe. These are the things that come up a lot. And you come up with this, and if you don't know how it compares to these things, then it's just like a shooting star out of nowhere. So the reason we want to go back to here is because we know where it fits in. We know that it fits in between n and n squared in a nice place called n log n. That's a good question. It's just that log n factorial to some people might not give them a sense. Maybe you'd think this is exponential or something, or who knows. Okay? That's a good question. Other questions? All right, let's go ahead and do this. Let's try to analyze log of n factorial. We want to show, number one, that it's less than or equal to some constant n log n. And then we're going to have to show that it's bigger than some other constant n log n. This will be the big O part. This will be the big omega part. All right, so this is going to be a lot of algebra and some math. And stick with me here because there's one clever idea. Let's do the first part because it's easier. What constant could we use here, and how could we get any handle on this at all?
Constant is 1.
Sam says it's 1. We believe Sam, right?
You can raise log, take the n to the log n to the n. Log rules.
You could do that. I see what you're thinking. That's a good idea. That's a good idea. That's a good idea.
Factorial is obviously less than n to the n, because each of the terms is n or less.
All right, let's go with your idea. Sam and Michael say that log n factorial is less than or equal to log n to the n. Everyone agree to that? Because this is just n times n minus 1 times n minus 2, and this is n times n times n times n times n. So here are all the terms. Each one is bigger than each of the terms here. So I agree that this is definitely bigger than this, because n to the n is bigger than n factorial. And if you remember your log rules, this equals exactly n log n. So log n factorial is less than or equal to n log n, so I could use the constant 1. And Sam's right, and Michael's got a good way to look at it. So let's go with your way. I wanted to do it a little bit of a different way because it leads to the next problem, which is much harder. The way I wanted to try to show you how to do it is, let's use the other rules for logs. And you got to remember back month 0 now. How do you do logs? Let's expand this a little bit. What's the log of n factorial?
Log n plus log n minus 1, so on.
Right? These are all multiplied, so if you run the log through it, you add all the log values together. Plus log of 2 plus log of 1. All right, there it is. That's log n factorial. We want to show that this is bigger than or equal to some constant times n log n. We've got to pick a constant to make that work.
Lop it off in the middle.
Joe, sorry, what did you say?
That's if you combine all those terms, it becomes n log n.
I don't think so. If you combine all these terms, it becomes log n factorial, right?
Well, combine
Yeah,
all
Doug?
of them except for the log n.
Except for this?
Yeah.
That-
And then we can divide both sides by log n. And we're going to have 1 plus...
And to the left side's log n factorial.
We'll get log of n minus 1 factorial divided by n or something like that. Maybe.
Plus log of n minus 1 factorial. It would be equal to...
You're
some
dividing by
constant times
log
n.
n? You're dividing by log n? That's a lot of trouble.
It's a lot of trouble because you get log n minus 1 divided by log n minus 2
No,
divided
you
by...
group those guys back together.
So you get log n minus 1 factorial.
Right. And then you divide
So you get 1 plus log n minus 1 factorial is greater than or equal to C1
Times n.
times 1. Right, but you get log n minus 1 factorial over log n. That's kind of ugly.
Well, you
Well,
combine
if
those.
you divide log n factorial by log of n, you just get the factorial. They all cancel out except for the exclamation point.
Well, let's get back to this question. What should this C be? Is 1 going to work? 1 works for less than or equal, so it's unlikely 1's going to work for greater than or equal. You want a number bigger than 1 or smaller than 1 here? Smaller than 1, because you need it to be bigger than this value. How much smaller than 1 do you need? Look, you can just guess. You can't pick 0. That's not allowed. You got to pick something which is bigger than 0. So you could pick, I don't know, you could pick a tenth, you could pick 100th, but it's just a stab in the dark. Let's get something that we think is going to work. And
Half will work, but 1/17 is so much nicer.
yes, 1/17 is nice. Let's see if we can get a half to work, but why would we expect a half to work? Why would you ever think anything's going to work here? Maybe it's not true. I mean, why do you think this is true? Why is it going to work? You want to cut this in half, Sam?
Cut it in half and then over 2.
All right, the reason, what I'm hoping you look at here is an idea that you've seen before, and you've seen it with the triangle numbers. What was one way to add up the triangle numbers? First and the last, second and the second to last. You got no guarantee that's going to work here, but at least it's something to try. Okay? One of the things you're trying to get in discrete math is a big bag of tricks. Okay, you came in with hardly any tricks, and you want to leave with a lot of tricks, and you want to be able to do 2 things. When you pull out a trick, you want to be able to recognize it and know what to do with it. So it's not like, oh, this is pneumatic double hammer. I don't know how to use this. Better put that back. Right? You want to be able to use all the tools in your basket, but you know what makes you really good? What makes you really good is you see this big complicated machine and you say, oh, I know the tool that's going to open that machine, and you go right in and you grab it. That's the hard part. But minimally, what you should expect to get is, I know every tool in my chest, and I know which ones more or less are helpful. So here, let's try this tool, whether it works or not, before we guess the constant. So here's what we do. We have log 1 plus log n. Log n minus 1. Is this a good way to pair them? Plus log 2. Is that all right? Well, we can try. What's the middle term going to look like, more or less?
Log of n over 2 plus log of n over 2.
More or less like this. We just chop the thing in half. This is what Sam suggested because he has good intuition about these things. He's done a million of these things, and he's got a great bag of tricks. So he had a sense this would work, and maybe it was going to work, but let's look at it. We've got these things all paired up. We've got half as many pairs here as we had terms up here, and each one comes in 2. Log 1, log n minus 1, log 2, and the middle terms are log n over 2, log n over 2.
Can you explain how that is the middle term?
Because as you get to you're going 1, 2, 3, all the way up to n. So the middle term is going to be halfway, n over 2. The question,
There's only one of them.
right, what if there's an odd number of terms, and these two will differ by 1?
Okay.
So you know what, I should say fudging here a little. You're right, Sharon. I mean, I should really be very careful about this. If it's an odd number of terms, this misses a little. But it actually won't affect our argument, so it won't hurt.
There would never be 2 identical terms, right?
That's the right way to write it. This round,
He's pointing out that, I see, okay, fine.
you round up, you round down. That's actually right. But you try to do an analysis with this, and the analysis becomes harder and kind of obscures your main idea. But if you want to be very precise, round up here and round down here. That, I think, works fine. But let that go. Don't get involved with the details. Work the details out later if you get the main idea first. We're still not even up to the constant part. We're not even close. What's going on here?
Log 1 plus log n is log n. Log 2 plus log n minus 1.
This is log n times log 1, so that's log n. This is log 2 times n minus 1. This is log 3n minus 3, and the last one is log minus 2, thank you. And the last one is log ... n over 2,
More or less.
more or less n over 2. Okay, so now we've got it written like that. How many terms are here altogether? N over 2 terms, right? Half as many terms as we had before. That's a clue that we should try to put a 1/2 here. Right? That's a clue, but where do we go next? We got log n here, right? We got log of something here. Don't know if it's bigger than log n or smaller than log n.
N minus k times k has as its maximum k equal n over 2. Those products are going to go up to n over 2.
Okay, we can do something a little, that's true, but we can do something a little bit, we can avoid even if you didn't know that. What if you didn't have that in your bag of tricks? This is bigger than 1/2 n log n over 2. And let me try to explain why. Let's do this piece by piece. How do you know this part is bigger than log n over 2? Because it's n over 2 times something, right? How do you know this one's bigger than log n over 2? Because one of these two, either 2 or n minus 1, is bigger than log n over 2. Right? You have 2 times n minus 1. One of them is going to be bigger than half of n. 3 of n minus 2, one of them is going to be bigger than half of n. So every one of these terms, this one, this one, this one, every single one of them is bigger than log n over 2. Does everyone agree with that? I have too many confused faces. Let me say it again, because this is an easy idea if you just think about it for a second. What's going on here? I got these numbers going from 1 to n, and these numbers going down from n minus 1. So 2 times n minus 1. One of those numbers is bigger than half of n, right? So this is log 2 plus log n minus 1, right? This one alone is bigger than log n over 2. This one alone is bigger than log n over 2. That one alone is bigger than log n over 2. Who doesn't get it?
So we didn't need the third step, really.
No, maybe this wasn't the best way. Maybe. Yeah, question.
One thing, which is just why you're multiplying.
Why we did this step?
No, how you're getting to log 2 times n minus 1 from. Is that just something you can do with logs?
If you add 2 logs together, then it's the log of their product. But following on that line, I mean, we did this because someone suggested it, but now maybe we didn't need to do it. Look back here. Each of these pieces is something that adds up almost to n, right? So one of these two, either the 2 or the n minus 1, is bigger than half of it. Here it's n and 1. This one's bigger than half. Here it's n minus 2 and 3. One of them is going to be bigger than half of n. So each pair of these, each pair is bigger than log of n over 2. And how many pairs are there? There's n over 2 pairs. Yes, Sam, what do you want to say?
Can you give me a minute on the board to show it much more clearly?
All right.
Or afterwards.
As soon as I'm done, you can have 5 minutes and show it more clearly. All right, so here's where we're up to. We have this original log n factorial. It reduces down to here, and now I know it's bigger than a half n log n over 2. Are we done? Almost.
We have to write log of n over 2 as log n minus 1.
Log n over 2 is log n minus the log of 2. So if I multiply this out, I get n over 2 log n minus n over 2 log 2. n over 2 log 2. Log 2 is just a constant. It's 1. Log base 2 of 2 is 1. So these two are the same. So I've gotten the number a half. I've shown that my sum is bigger than n over 2 log n, but it's bigger than n over 2 log n minus n over 2. And I don't want that minus n over 2 in there. I've got to get that out of there. So there's one extra little step, a little fudge step I have to do here. And here's what I do. I note that this part here with the negative is actually bigger or equal to n over 4 log n, as long as n is past a certain number, as long as n is bigger than 4. You could check this part yourself by doing the algebra. So what constant actually works in the end? The constant that works is a fourth, as long as n is bigger than 4. And you might be able to get away with a half as long as n is past something, but I didn't bother trying to calculate what that past spot should be, so instead I just changed it to here where the algebra is easier to do. All right, I rushed through that at the end, but the upshot of this is that log n factorial is big theta n log n. The upper bound big O part is easy to do. The gamma part is much harder to do. It requires a lot of algebraic manipulation. Sam's going to show you an easier way in a second. It ends up being bigger than n over 2 log n minus n over 2, which is bigger than or equal to n over 4 log n. So the c is a fourth, and the n0 is 4, or the x0 is 4. Donna, question?
Did you mean omega? You said gamma.
I meant omega. There's no gamma. Alpha, delta. I was thinking of a frat. Teresa.
Where did minus n over 2 come from in the box?
I did this quickly too. Log of n divided by 2 is the log of n minus the log of 2. Okay? So it's a half n log n, that's this, minus a half n log 2. Log 2 is just 1. Log base 2 of 2 is 1. So that's minus a half n. That's a good question, Teresa. I really went through that way too fast. But that's true. And it's just that stupid minus a half, so we make the constant a little smaller to handle that.
So all of our logs are log base 2 here?
In this particular case, it actually is a binary tree, and it really is log base 2.
But in order to do that, you have...
If we didn't happen to know it was log base 2, then at this point it would be n over 2 times some constant. Right. All logs are a constant factor multiplied by other logs. So if it was base 10, then I just have it a little number there, not n over 2 times some other number, and it wouldn't affect the details too much. Are there other questions? All right. So Sam, I'll give you 5 minutes right now. Yeah, Baruch, quick, yeah.
I see what you did. I think I followed, but intuitively it doesn't play well with what I see on the board. I mean, you have log n plus log n minus 1 plus log 1.
All this, yeah.
On one side. On the other side, you have log n plus log n plus log n plus log n.
No, divided by 2.
No, but what you're trying to show is that this is greater than n log n, right?
Greater than some constant times n log n. So I'm going to use a half for that constant. It's not bigger than n log n itself. That's true. It's bigger than half of it, though. It's bigger than some constant fraction of it. The constant that I ended up using here is a half. So you're...
I know.
Okay.
That constant will do it for every n. Larger than certain n doesn't...
That's true.
Intuitively doesn't...
Oh, you wouldn't believe that.
I don't believe it.
Oh, okay. But it's...
I don't believe it. So I don't know what the trick here, but...
Okay, so before Sam does 5 minutes, I'll just say I'll give you my little story about Believe It. I was in, 10th grade or something, and there was a kid in my class named Bodner, Amos Bodner. And math was a little challenging for Amos, and he studied his head off for this New York, some standard exam that you had to take. And you had to pass this to get on to the next class. And he was one of these nervous kind of people that was always worrying about it. He would study hours and hours. It was just horrible to watch him suffer this way. And he was ready and ready. And he wasn't the most likable kid either, so you didn't really feel so sorry for him. And he would work and work and work and work. He wasn't a happy kid. So anyway, he took this... He took this, I wonder where he is today.
He's watching you on the
Oh, no! It just shows you how oblivious I am. The names have been changed to... I should have changed his name. Anyway.
You can bleep it out.
Oh, gee. Edit. No, anyway. So he took this test, and the teachers, calling out the grades, and the teacher said, well, everyone has a choice. I will say your grade out loud, or you can come up and look at it here. All right, so everybody, comes to them, and they make a decision, out loud or not, and whatever. So it finally gets to him, and he sits there squirming in his seat. Oh, I don't know if you should say it out loud. Oh, maybe you should. And he goes back, and everybody in the class is going, shut up, just a second. Finally, he says, tell it to me out loud. And the teacher, with a completely straight face, you needed a 65 to pass. The teacher reads his grade and says, Bodner, 64, and stares at him like this. Everybody thought he was joking, because he's a funny guy, the teacher, and he could conceivably have done this. So Bodner goes, you're kidding. I don't believe it. I don't believe it. And he's freaking out saying, I don't believe it, I don't believe it. And the teacher's not cracking a smile yet. So we're thinking, oh my God, it's like completely like not a joke. So the teacher goes, is it really true? And the teacher goes, 64, Bodner. So at this point, he's like virtually in tears and he's freaking out. And he says, I don't believe it. And he doesn't shut up and he keeps over and over again, I don't believe it. I don't believe it. I don't believe it. So finally, the teacher, never cracking another face except his little pursed lips telling him 64, looks at him and says, well, believe it, Bodner. And that was the end of the story. So anytime anybody asks me and says, like, I don't believe it, it's like I always think of that story. And now the whole world knows it. And then,
so did he really get a 64?
So he really got a 64. Well, believe it, Bodner. Oh, poor guy. Anyway, here's your 5 minutes. I'm done. I'm done blabbing. Yeah. I don't know which way Sam's going to do, but maybe if Sam has a better way here, you should see it, because he often has a better way.
N factorial is n times n minus 1 times n minus 2 down to 1. To get an upper limit on that, we substituted for each of these terms n itself. So n factorial is going to be less than or equal to n to the n. We really don't have to put the equal in. But now we want to get a lower limit on that. If we simply substituted 1 for each of these, it's not going to be a very useful lower limit. But I'm suggesting that we cut it off at, let's say, n over 2, and then it keeps going. Well, n factorial is going to be greater than 1/2 of the front tail, because we've cut off the rear tail and not only added more. It's going to be greater than n times n minus 1 all the way down to n over 2. And now I'm going to substitute n over 2 for each of these terms. Each of these terms is greater than n over 2 or equal to it. So n factorial is greater than n over 2, and there are n over 2 such terms. I'm fudging a little because n over 2 may be halfway in between two integers, but the fudge you can work out for yourself. So log of n factorial is going to be greater than log of n over 2 to the n over 2, which is n over 2 times log of n over 2, which is 1/2 n log n minus log 2, and log of n minus log 2 we dealt with before, but anytime you have a sum of two terms or a difference of two terms in which one term overpowers the other, you can effectively ignore the second term. So this gave you the 1/2 n log n. Again, instead of substituting at the end, where you have to substitute 1 for all of these terms, and that's not going to give you a useful inequality, you cut it off halfway and you substitute the left side by its lowest number, which is n over 2, and you're going to get as a lower bound n over 2 raised to the n over 2 power. Exactly the same as the upper bound was n to the nth power.
Good. I think that's easier to see. Sam is basically showing it to you before you take the logs on both sides, and then takes the logs on both sides at the end. And it is easier to see that way, I think. Sam also mentions this. He says, look, if you have n over 2 log n, and then there's a minus something, since n log n is bigger than n, you can just forget about this minus n over 2, because as n gets big, sooner or later, this will overpower that. And that is true. But if you really want to use the theorem specifically, you have to say at what point that's going to overpower. That'll be that x0. Or else you just can do this little trick that I did, which is fixing the the C.
That's the version of 17. Always is overpowered by 17.
That 17 would work here, right? Okay, so let's quit.